So, this is another initial condition we have defined. So, based on these assumptions, we will move forward and we will take a look at the remaining part. So, this is the time derivative part of the TDSE and this is the right hand side of the TDSE. This right hand side of the TDSE can be written as follows. I can explicitly write down as H naught, then just insert the wave function. The wave function in this quantum decay dynamics we have used e to the power minus I En t by h cut n plus 0 to infinity Cmt e to the power minus I Emt by h cut m dm plus this part also. One can write it down. And if we do that, then finally we have to equate, because it's a TDSE, we have to equate the left hand side and right hand side. If we equate them, then what I get here is that this part would be equal to this part, and one can now use this, employ this operator on this n state, and we know that it is going to be eigenvalue equation. Again, this operator on this m state will get the eigenvalue equation, and if we do that, then we have following terms: I h cut dt e to the power minus I En t by h cut n plus Cnt e to the power minus Ent by h cut n plus I h cut 0 to infinity dCn t dt e to the power minus I Emt h cut m dm plus 0 to infinity Cmt em e to the power minus I Emt by h cut m dm. So, this is the left hand side, and right hand side would be Cnt en e to the power minus I Ent by h cut n plus 0 to infinity Cmt em e to the power minus I Emt by h cut m dm plus Cnt e to the power minus I Ent by h cut h dash n plus 0 to infinity Cmt e to the power minus I Emt by h cut h dash m dm. So, we can see that there are few terms which will be cancelling out. So, this term em term, this term will be cancelling out, and this term, here I had another term En, so this term will also cancel out. So finally what I get is this expression. Now we will reduce it further. We will do one thing. We will first multiply by this from left. And then the same equation will multiply by m, so this is going to be complex conjugate of that m from left. So these are the two mathematical tricks we will use, and this is something which we haven't done in the time dependent perturbation theory. In the time dependent perturbation theory we haven't tried to obtain a couple differential equation which we are trying to do here. But up to this point the derivation steps are quite similar to the what we have used in time dependent perturbation theory. So if we do that, if I multiply by n by from the left, and if I multiply the m from the left, then one can easily deduce this this following thing, making some using the assumptions we have made. Assumption is not orthonormalization condition which we can use, and also we can we assume that the state are not getting coupled with itself. So those assumptions we will make, and then we will be able to reduce it following way. So if I use this, then I get this equation I h cut dCN t dt equals 0 to infinity CMT e to the power I En minus Em t by h cut n h dash m dm. So this is one equation we get, and if I multiply this one, then I get following equation I h cut 0 to infinity dCm t, this is m dash dt e to the power minus I E m dash t by h cut m dash dm dash equals Cn t e to the power minus I En t by h cut m h dash n. That's the equation we get. So if I so what we have done here, when you are multiplying this equation with this m, the complex conjugate of this state, then what we have used is that within this integration the variable we have used as m dash to distinguish it from the state by which I am multiplying. So this is just a convenient way of representing the integration. We don't want to mix up two different m's here. Here we are multiplying by a particular state m, this m is a particular state, and that's why integration is running over the m states. In the integration. So we know that this equation can be further reduced, because we know that we assume that this m dash is 0 for all states except for not for m equals m dash. So this entire integration becomes 0 except for one term, and the term is going to be m equals m dash. And that, if I use that condition, I'll be able to write down I h cut dcm now. This is going to be m dash equals m now, dt e to the power minus I e m now. Because m equals m dash equals m now, divided by h cut equals now cnt e to the power minus I ent by h cut m n. So this is the reduced form of this expression for this part of the expression, which can be again further reduced as I h cut dcm dt equals cnt e to the power I em minus en t by h cut m n. So what we get finally after doing all these things, we get two differential equation, coupled equations. One is depends on the other. So these are the two coupled differential equations we have obtained after inserting that initial trial function, wave function, to the TDSE. And if we have these two coupled differential equations, question is, how do I solve these two equations? Because our target is to find out CNT. We want to find out how the population in the initial state doing as a function of time. So that's exactly what we are trying to find out. So what we should do here is that we have to find out, and to find out this population. So from this equation I can get it, but the difficulty in this derivation is that I have to find out an expression for Cm, then only you'll get that. And Cm expression can be obtained from this equation. So from this equation I get that Cm expression, I insert that expression here, then I will be able to integrate this equation to get the population in the nth state. That's exactly what we are going to do. So let's integrate this part. We'll be able to integrate this part very easily. It is going to be nothing but Cmt minus Cm0 equals 1 by I h cut 0 to t. I keep it t right now. Then this is going to be Cn. I make it t dash now because it is now variable within this integration to separate, to distinguish the limit from its variable of the integration. And e to the power I em minus en t dash by h cut, then this h mn integration dt dash. So this is the integration I have, and we know that this Cm0 by initial condition, I have assumed that the no population was present in the final state. So this is going to be 0. So this part is gone, and I have this expression, this Cmt expression like this. And what we need to do, as I have mentioned before, this expression now needs to be inserted here so that I can get the expression for this. So what I'll do right now, I will insert it. If I insert it, then what I get is 0 to infinity 1 by I h cut 0 to t Cn t dash e to the power I Em minus En t dash divided by h cut, then h mn dash, then dt dash. That's the first integration Cm, and then remaining part is here. This remaining part in the integration is here. That is going to be, I will write down e to the power I En minus Em t by h cut and then I have this h n m then dm. That's the total integration I have. So it's just rewriting. If I rewrite this one to some extent, I get this this form, the integral differential form of this equation, where I have this change in population. This integration, what I get here is that change in population, this expansion coefficient as a function of time, and that is given by this entire expression. This expression is an interesting form. It is a differential form. This is differential equation. Definitely it's a differential equation, but at the same time this differential equation depends on the entire, so this is the differential equation. This derivative depends at time t. This entire derivative at time t depends on this integration over time t. So time derivative, so basically this equation shows that time derivative of Cnt at time t depends on the entire history of evolution of Cnt. This is Cnt from t equals 0 to final time t. Because it depends on entire history, that's why it is called integral differential form of the TDSE. It is the same TDSE form, but it's an integral differential form of the TDSE, assuming that the wave function was expressed as a linear combination of the initial state and all final states. We will stop here and we'll continue this discussion of this integral differential form of the TDSE in the next session.